Okay, let's talk now about mixture of Gaussians. Again, suppose that we are given a training set with m input vectors of dimension n, and we want to model the data by specifying a joint distribution, a joint probability distribution of x and z. Consider z as the cluster or label indicating the kind of point that vector xi is. So we will consider that there is this joint probability distribution of x and z, and this joint probability distribution can be written also as the probability of x given z times the probability of z for every example I. Here these variables z are to be considered as multinomial given a parameter phi, where this phi for every j will be 0 or larger than 0, with the condition that if you sum all these phi or phi parameters from j1 to k, this sum should give you 1. So j is an index over each of these parameters phi, and k is the number of, let's say, possible groups that exist in this data set, like the number of clusters. So we will specify for every example that for every example you will have a probability j, which could be 0 or higher than 0, to belong to a certain extent to some cluster j. So the parameter phi j gives the probability that the label of the example I equals j or is j, and the probability of x given z equals j. Here we are assuming that it is drawn, or it can explain using a Gaussian or normal distribution with some mean mu j and some covariance matrix sigma j. So suppose that we are talking about k equals 3, so we're talking about 3 Gaussians. Gaussians can look like this. These are defined in a two-dimensional space, and here we see some probabilities 0.5, 0.3, 0.2. That is the probability that one of the points belongs to the Gaussian in red, 0.3 that they belong to that this point belong to the Gaussian green, and 0.2 of probability to belonging to the blue Gaussian. So as we said, the joint probability of the input vector x and the label z can be written as the product of the conditional probability of x given z times the probability of z. And we, as I said before, we let k denote the number of values that the z's can take on. So all the possible clusters that we will consider, k clusters. Thus our model posits that each x was generated by randomly choosing zi from the possible from the set of possible clusters from 1 to k, and then the x was drawn from one of k Gaussians depending on the value of z. This is called the mixture of Gaussians. Note that these are latent random variables or hidden random variables, meaning that they are unobserved. So we don't have this information. Remember that the only information we are given is the set of input vectors, the set of vectors x, but we are assuming that each of these vectors belong to a group that we don't know how many groups are, and we don't know these assignments, but we assume that this information exists in the way of a random variable, and we are calling this a random variable z, but it is a hidden or unobserved random variable. In this case, the parameters of our model are phi, mu, and sigma. Phi is the probability for assigning the values of these different z's, and mu and sigma are parameters of the conditional probability modeled as Gaussians. So to estimate these parameters, we write the likelihood, as we saw previously in expectation maximization, the sum for every observation m, for every input vector m, of the logarithm of the probability of x with parameters phi, mu, and sigma. And when we introduce the hidden variable, the z variable, we will get here a joint probability, and that joint probability can be written as the product of the conditional and the probability of z. Mu and sigma, as you can see here, are the parameters of the conditional probability of the Gaussian function that is going to model the values of x, and phi is the parameter that will tell us the values of z. So if we set this likelihood function, the log likelihood function, to 0 and compute the derivative to try to maximize it, which is what we want. We want to find the parameters phi, mu, and sigma that will maximize the probability to observe what the data we have given. We will see that it is not possible to do that analytically because we don't have the information about z. Remember that this z is one that we are introducing here, but we don't have any observations from z. We have only observations about x. This random variable z indicates which of the k Gaussians each x had come from. If we knew what the z were, the maximum likelihood problem would have been easy. We can write it as this if we had z, and solving this will give us this way to estimate the optimal phi, mu, and sigma if we had the hidden variable, and this is simply the Gaussian discriminant analysis. But since we don't have z, we cannot solve it like the Gaussian discriminant analysis, and what we can do is to follow the expectation maximization algorithm in 2 steps. In the E step, we will guess the values of z for every observation I. Okay, like in k-means, initially you just assign to each of the observations one of the possible centroids, and in the M step we will update or recompute the parameters of our model. In this case we have 2 probability distributions, the conditional one and the probability of z, and our parameters are 3, phi, mu, and sigma. So the algorithm is this one for mixture of Gaussians. In the E step we will assign values to W. You see here that you will have for every cluster, for every j, and for every point you will have a probability, which is the probability that the group the example I belongs to is the group J or the cluster J, given the value of the input vector and our parameters. So these parameters, in the very first step, when you implement this algorithm, you run this algorithm, these parameters are to be assigned randomly. Of course, verifying that the values assigned make sense, given that this is a mean vector and that this is a covariance matrix. So once you have initialized these parameters, you can compute the probability that for each of the examples I, what is the probability that that example will belong to the group J. Suppose that you are talking about 3 clusters, J will be 1, 2, and 3. So you will assign a probability to each of the examples to belong to cluster 1, another probability of this point to belong to cluster 2, and another one for cluster 3. So this is called a soft assignment because in k-means each of the points of the I points were assigned to only one of the clusters, only one centroid. In this case, each of the input vectors will be assigned to each of the clusters with some probability. Okay, and of course at some point the probability could be 0, but initially you will have some probability to belong to each of the clusters. That's why we have this plot here. Like, for example, suppose that a point belongs to this cluster with probability 5, to the green one with probability 3, and to the blue one with probability 2. Okay, so they will have a probability to belong to each of the clusters. So once we have initialized the parameters and we have assigned the first probabilities, the first soft assignments, we go to step 2, which is the maximization step, and here we need to recompute the parameters. So in k-means we had only one parameter, which was the mean. In this case we will have the parameters phi, which are the probabilities of selecting each of the Gaussians, the mean parameter that will define our Gaussian, one mean parameter for each of the Gaussians that we are considering, and also we need the covariance matrix for each of these Gaussians. So if we are talking about 3 clusters, we need 3 Gaussian functions, and therefore we will need 3 mean vectors and 3 covariance matrices. And here are just the formulas to compute them, which are exactly the same that you used in Gaussian discriminant analysis. So what we are doing here is that we are defining or estimating 3 Gaussians in this example, and the final probability, the final joint probability, will be a mixture of these 3 Gaussians. Okay, so it will look something like this. So given a point in this 2D space, you will compute, suppose that the point is here, the observation X is here, you will compute a probability, and given this probability using the Bayes rule, like in Gaussian discriminant, you will classify that point or assign that point to each of the groups, to each of the clusters represented here by each one of the Gaussians. Okay, so if you remember, in k-means the assignment of one point to a group depends only on the distance to the centroid, which is the mean vector. In this case, we are not considering only the distance, but we are using a probability model. So here the chances to belong to one cluster or to another cluster will depend on the Bayesian probability of belonging to that group given by the Gaussian distributions. So it's a more elaborate model, a more complex model. So once we have estimated parameters phi, mu, and sigma, as I said, we can apply the Bayes rule to classify a new point, and this is exactly what we did in Gaussian discriminant analysis, just considering which of the clusters is more probable. This algorithm is of course reminiscent of the k-means clustering algorithm, except that instead of having hard assignments to each of the centroids, we have soft assignments W. Similarly to k-means, it is also susceptible to local optima, so reinitializing the algorithm at several different parameters may be a good idea. So this is an example of a mixture of Gaussians with 3 Gaussians and 500 points. These 500 points were generated from 3 different Gaussian distributions, red, green, and blue. Initially, of course, we don't have the labels, so they belong to the same group initially. And after you have run the mixture of Gaussians algorithm, this is a solution that the mixture of Gaussians is giving you. And as you can see, it is not perfect. There are some points here that were assigned more to the green group than the red group. And if you notice, there are some blue points here that finally, given this probability distribution, were assigned to with higher probability to the group of the greens. So of course there are problems in which the perfect solution is not possible to obtain. Here is a very visual run of the algorithm, so you can have a more intuitive idea of what is going on behind this algorithm. So here in this example, we have initially each of these circles represent a point, and you can see that they have 3 colors, green, red, and blue, and the size of the arcs of the colors represent the probability of belonging to that Gaussian, to the red Gaussian, to the green Gaussian, or to the blue Gaussian. And you see here the initial Gaussians. The green one looks more like a circle, and the red and the blue are quite similar between them. So for example, this point here has a larger arc of color green, representing that it has a larger probability of belonging to this Gaussian, this green Gaussian. And if you look at this point here, it has a slightly larger arc in the blue, but the size of green, red, and blue are quite similar. So at this point, which is the initialization point, it is impossible to assign with high probability this point to a specific cluster. So in iteration 1, after you have made a guess about the Gaussian it belongs to, or probabilities of belonging to each of the Gaussians, and after re-estimating the parameters phi, mu, and sigma, the sizes of the arcs have changed, and also since you have updated the means and the covariances, the matrices, also the contour, the main contour of the Gaussians are different now. in a second iteration, the arcs continue to change. Iteration 3, and you see that in iteration 4 these points are more defined. These are more defined now as belonging to the group of blues, and it is getting more defined as you go on the iterations. This is in iteration 5, and this is in iteration 6, for example. And you can see now that if you want to classify these points, the largest probability is to be green, and this the largest is to be blue. These ones over here have a larger probability to be red, but these ones in the border, at this moment they are still classifying this as green, but it could very easily be also red. So these points that are in the boundaries of the probability distributions are the ones that are difficult to classify perfectly. And this will be in iteration 20. Okay, when these Gaussians are more defined, then the final classification would be something like this. So as you can see, the goal is the same as k-means, to assign each of the points to a group. In the case of k-means, we make a hard assignment, so each point will belong only to one group. And here in this case, you will assign each of the points to each of the groups with some probability. And as the algorithm goes on, the estimations will be more precise, and the probabilities of belonging to the main group will be the largest one. So this is all about expectation maximization and k-means and mixture Gaussians that we're going to study. I hope this is useful. Thank you, and talk to you later. Bye.